Cool. So I guess part of the thing about streaming and getting lectures recorded, probably has to do with liability. Maybe some professors are thinking, if my lecture is recorded, then what I say can be used. If somebody wants to kind of accuse me of something.
Pico's like that. He will not let you record or take pictures or anything.
But my solution to that is to record so many things that it is difficult to see through. So the signal to noise ratio is kind of problematic there.
Like I have hundreds of hours online to watch Mike's stuff.
No- Huh? There's no description in the title either. So they just have to kind of go through every single one. But one of these days it's easy to do it, because of the closed captioning. So a bot, an engine can do that. Just look for the closed captioning and look for specific words like CIA, KGB, the president, that sort of thing. Secret Service, the NSA, huh? Cybersecurity. Just the other day, I was talking about cybersecurity in the 80s and the 70s. That basically involves somebody using a box of floppy disk to club somebody else. That's cyberbullying right there. Yeah. Hmm? Or you use epoxy to epoxy shut the floppy drive door. That is cyberbullying, definitely. Back in those days. All right, so what we'll do today, the first thing is to look at the solution of the Fibonacci number question. So even if you got it done, it still doesn't hurt to kind of watch how I do it. Maybe your solution is the same as mine. Maybe it's a little bit different. It is possible that yours is different, but it still works. Okay, so there are all of those possibilities. But this will be a great time for you guys to ask questions about that particular homework assignment. All right, so we'll get started with that one right away. And I'll write the C code just so that we know what the program is supposed to do, and then we'll implement the assembly code for that. So the C code has the Fibonacci number taking a single argument. Okay, we call it n. And then it has a single return statement and has a ternary operator. So if n is less than 2, then we return just n itself. Otherwise, we return f of n minus 1 plus f of n minus 2. And that's it. That's how Fibonacci is expressed. And then we have the usual main. Okay, so this is just main itself. It has a local variable that is an unsigned a-bit integer. I think I called it x in the C code. And then we just say x equals to f of something. I believe f of 13 is the largest Fibonacci number that can still be stored in a bits. So if you go for f of 14, the program is not going to break. It's just that the number that it is returning is no longer correct because we are only returning 8-bit numbers. Okay, and by the way, this will take a while because this particular implementation of Fibonacci number is exponential. In other words, f of 12 is going to take approximately half the time of f of 13, and then f of 11 is going to take half the time of f of 12, and so on. So f of 13 is going to take a little bit of time. Okay, all right. And I'm going to write this one, this way, just not only because it makes it a little bit more clear, but also because I want a little bit more space to the right-hand side for the assembly code. So this way, my assembly code is not going to interfere with the C code. All right, so we'll open up another mousepad window to express the assembly code. So the assembly code starts with subtract dd to initialize the stack pointer. Once again, it is not exactly needed, but I just want to express the importance of initializing the stack pointer. And then we jump to main, so this way I can preserve the ordering of the subroutines. So the first thing I want to do, I'm just implementing f first, and then we'll implement main. So at f, I want to express what is on the stack. We have n on the stack, and then we have the return address on the stack, and the stack pointer, register D, is pointing to the return address itself. I'm just checking the recording stuff here. It is recording, and let me just double check OBS. It is also recording. Okay, cool. All right. So what we need to do first is to get to n so that we can compare n to 2 and then decide what to do with it. Now, this is something that's important. In a function, the only thing you can count on, there are two things. One is the stack pointer. And the second thing is what the stack pointer is pointing to, and possibly what is around that, okay, on top of that. So in this case, the only thing you know is the stack pointer, D, is pointing to the return address. And on top of the return address, which means the next memory location, has the parameter n. That's all you can count on. Is that okay? So that means every time you want to get to some parameter, you have to start with the stack pointer. Okay? So that means, in this case, I'm doing there's a quicker way to do it. CPR, is it works, but it's not the quickest way to do it. In this case, I can do, well, in this one, it's about the same, but I'm going to show you the alternative way to do it. I'm loading 1 into C, and then I'm adding D to C. It accomplishes the same thing as CPR, CD, and then the increment C, but this one is actually less efficient, but it accomplishes the same thing. Is that okay? So even though, I'm not expecting you guys to find out what is the most optimal sequence to get something done, if I present two sequences that can get the same thing done, I expect you guys to be able to recognize that the two sequences can do exactly the same thing. Is that all right? So that's why I show you, variations of ways of doing the same thing, so that you guys can kind of get used to that. Okay. So I also want to express what is C at this point. C is not n. C is the address of n. So this is the kind of one of the most important part is by computing something, by adding something to what the stack pointer has, you are computing the address of something on the stack, but not the actual value of that thing. Yes?
Don't you need to CPR CD?
Huh?
You never did copy register.
I don't need that anymore, because in this case, it does the same thing. So this is equivalent to CPR CD and then followed by an increment C. I'm just doing the addition in a slightly different way. So I'm putting a 1 into C first, and then I add whatever D has to C. So I still end up with D plus 1 in register C. It's just the sequence of operation is different. This particular sequence of operation is really good when you want to have like 5 bytes from what the stack pointer is pointing at. Then this works really well because you're not incrementing 5 times. All right. So what I'm comparing in the condition of the ternary operator is not the address of n. I'm not checking whether the address of n is less than 2. I want to know whether n is less than 2. So to get to n from the address of n, I need to dereference. So that's why I need to do an LD. Whoops, wrong window. So that's why I need to do LD into some register. I don't think I need C back anymore, so I'm going to overwrite C with whatever C points to. So at this point, C becomes not the address of n, but actually n. Then we can compare. So now we have to do LDI, A is fine, B is fine, pick one register. Anytime we are not comparing with 0, we actually have to go through this trouble and use one register to specify what we are comparing to. So now we can use a JCI instruction. We know it's going to be a JCI instruction because I need to check a less than condition. Okay? So, but the question is, where do I want to branch to when A, which is representing the value of n, is, oops, I got it. Sorry? Oh, right. I need to compare first. So I need to compare C, which is N, with A. Okay, I think there was a reason why I wrote this first, because I need to determine, do I want to say compare CA or compare AC? Okay? In the original code, I want to see whether N is less than 2, and register C has the value of N, register A has a value of 2. So if I use JCI at this point, it will branch if and only if N is less than 2. So that matches what I want to do. Now, if you change it, it will still work. You can still use some sequences of conditional branches to make it work. But this way, it is a little bit more clear, easier to kind of figure out what we are doing. So now we have to figure out where it is going when N is actually less than 2. So I'm just going to say, this is going to a label called then value. Okay? And then we have an unconditional branch to the else value. The naming of these two labels has to do with the middle part of a ternary operator is called the then value, and then the last part of a ternary operator is called the else value because they correspond to whether the condition is true or not. Okay? Now there might be things we can simplify a little bit later, but I'm not concerned about simplification or optimization at this point. All right. So with these two branches, JCI and the JMPI and conditional branch, now I can define these labels. Okay, what do we do when we are at the then label? Well, this reminds me that I can make this code a little bit more optimized. Because right now, if I were to use this code the way it is, I have to do a copy register. Because the return value is supposed to be specified by register A, but register C has the actual return value of N. So it's no big deal. We just need to copy register C to register A so that it becomes the return value. But if I use my registers differently earlier, I could have saved this one single instruction. But as I said, not too concerned about efficiency or optimization at this point. We'll just let it slide because unless this code works, I'm not going to spend my time to optimize it. So we'll basically specify this is our return value for the then case, okay? And then we have a JMPI instruction to go all the way to the end of the subroutine. So we'll call this the end of function f, okay, which is here somewhere, and then we'll figure out what to do over there. And then we have the else value, which is a different label. So at the else value, that is where the kind of nasty stuff is happening, right? Because we have to call Fibonacci, and then call it again, and add the two return values. All right, so let's see what we need to do. So the first thing we need to do is to pick one of those two, okay? You can call f of n minus 2 first. That's okay. If you want to call f of n minus 1 first, that's fine too. So with addition, I do not think the C compiler actually has a standard of it has to follow the strict order of left to right. Okay, because of two things. One is addition is commutative, and two, addition is not a logical operator. If it's a logical operator like or and, because of short-circuited evaluation, the C compiler is required to evaluate from left to right. But there's no short-circuited evaluation for addition, subtraction, multiplication, and that sort of thing. Well, I guess you can say for multiplication, there's a 0 case that can be short-circuited, but it's not part of the language specification. So in this case, I could choose easily to evaluate f of n minus 2 first, and that would not really change the final value that I'm returning. But I'm going to read from left to right and deal with n minus 1 first. So I have to push n minus 1 on the stack. Do I already have the value of n somewhere at this point? It's in register. It's not in register A. If I get to this branch, it is not. It's in register C, okay? So we need to subtract 1, okay? So we decrement C so that C is now n minus 1, and then we push it on the stack, which means we have to decrement D to reserve that space on the stack, and then do a st instruction to actually store n minus 1 on stack. So I'll just say push n minus 1 on the stack. And then we need to push the return address. So we'll do another LDI instruction, reuse register A. This is F, return from, I'm just going to say n minus 1. Okay. Long label name, but it says exactly what it is. So we have that label defined here. Return from n minus 1 over here. So if you're copying the code, it is going to be a little bit difficult because you have to kind of insert and insert and insert on the piece of paper. So I would just kind of focus on the projector because I'm pretty sure it's still being streamed. Yep.
What I do is I just wait until you write the rest and then I write the.
Yeah, you can do that too. Yep. Because this is exactly how I write my code. Okay, I do not write sequentially. If I start something, I write the end right away, and then I fill in whatever is supposed to go in between. Okay, so I decrement D, and then we push it on the stack. Okay, so we are pushing the return address in this case. So now that I have the argument and also the return address pushed on the stack, we can now continue execution at the subroutine. Well, it just so happens that this is the same subroutine that I'm in. It doesn't change anything. Doesn't change the way we push arguments. Doesn't change the fact that we are going to push a return address on the stack. And it doesn't change the fact that we are beginning at the very beginning of the subroutine. In other words, whether f is calling g or h or whatever other function or calling itself, we use exactly the same mechanisms. There's no difference whatsoever. Is that okay? So that's one thing that you can use to help demystify recursion. Because a lot of times, including myself, people think about recursion and go like, that's not possible because I'm in a subroutine that is being defined. It is not done yet. How can I call a function that is incomplete? Well, that is not the case, okay? Because we have to separate compile time issues from runtime issues. Okay, so continuing from here, I don't really care whether I'm calling myself or any other subroutine. I'm expecting to come back at this point. So when it comes back, we have to deallocate what we have just pushed on the stack, which is the parameter. But this time, so don't copy it yet, okay? So I do need to increment D, at some point because I need to clear that space for, other things that I need to push on the stack. But remember, when you return from a subroutine, all registers can be overwritten, can be clobbered, okay? So that means register A, register B, and register C may not contain what they had before the function call. Is that okay? So that means, even though register C had n minus 1 before the function call, it may not have n minus 1 at this point. I cannot count on that anymore. So, but I do need it back because I need to calculate n minus 2 for the second call to Fibonacci. Now, so I have two choices now. I have one choice and go like, yeah, let's just assume everything is gone, and then we just have to recompute the address of n, and then we decrement it twice, not the address of, but we decrement n twice, and then push it again on the stack. I could do that. That's what a compiler would do. But I'm tricky, and I'm going like, hey, the stack still has that argument, right? And that argument is what? N minus 1. So I could retrieve that. Is that okay? So I could use that trick. But that trick is potentially dangerous as well. Because a subroutine is free to change its parameters. In other words, in Fibonacci, if I don't implement it this way, I could, just do an n minus minus, somewhere, and that would change the actual parameter that is on the stack, and the caller doesn't know that the parameter itself has been changed. So that means, if I want to be tricky like that, I have to be very, sure that the parameter is not getting changed. The C code only says this is, a unsigned AB integer, which means, inside here, if I want to do n minus minus, somewhere, it's okay. C compiler says it's not a problem. Now, on the other hand, if I say this is const, which is actually more appropriate, then we have a better reassurance that n is not modified, but it is not 100%, because you can always cast a const variable to a non-const variable and then change it. So everything that you can do in C to enforce something, there's a way to get around it. That is the nature of C programming. So that means to be safe, okay? I'm not saying this is the only correct way, but to be safe, it is best not to rely on that parameter. You can, but it's best not to. All right, so I'm deallocating it and go like, okay, we need to recompute n minus 2. Well, it's no big deal. We know how to do it. We just have to do a, before we do that, there's something else that we have to do. Register A has the return value of f of n minus 1. So I better do something about it first, because I'm about to call f of n minus 2, which guarantees to overwrite register A. Because f of n minus 2 is also going to use register A to return its own return value. So I need to do something about register A at this point. I cannot store it to another register, because there's no guarantee that the next call to f is not going to destroy that particular register. So I cannot copy it to another register. I know for sure register A is going to be overwritten by the next call to Fibonacci. What am I going to do? Put it on the stack. Very good. So we have to do a decrement of D again. So this part is, I'm going to write it like this first, and then we'll go back and talk about this, okay? So we will store to whatever D points to the register A. So this is basically to save the value of f of n minus 1 on the stack. Now, you can probably tell that we are incrementing and then immediately decrementing, so that instructions can be removed together. Yep.
But when you called F, wasn't A overwritten with 2 on line 10?
Say that one more time.
So when you called F, because F of n minus 1, it calls F over and over until it's less than 2, and then, but it would be in register C, wouldn't it?
What is in register C?
The value that is returned by n minus 1.
Why would it be in register C? Because register is already overwritten as you do the recursion. Every single invocation of f is going to use C the way that I'm using it here. So that means by the time it returns all the way back here, C is not going to be what you expect it to be.
Okay, so the last thing that happened was line 23 and 24?
Line 23 and line 24 is the last thing that we do for this invocation. But then that invocation would also have its own invocation and so on.
Yeah, and so when that happens, it does line 10 and line 11.
Yes.
And so A should have a value 2 in it.
No. What about this? Okay, A has a value of 2, but then C is going to have a value of the parameter itself, and then it gets decremented and so on. So if I were to guess, all the way back from the recursion, n would be, register C would have a very small value, when it returns all the way back here. But the point is, you cannot assume how a register is going to be used by a subroutine. You just assume that it is overwritten. But what is overwritten with? Make no assumptions. Now, in this case, it's recursive, and that's why you can sort of do some analysis, but the general idea is do not make any assumptions. Just assume that it's already overwritten by some random values, and whatever you stored in those registers is gone. So you have to recompute everything that you need from the stack pointer. Okay? All right. So now that we have saved the value of f of n minus 1 on the stack, we now need to deal with n minus 2. So we do the same thing. Okay, so we have to do a LDI let's see, LDI, well, doesn't matter which register this time. So I'm going to reuse register A. I'm going to put a question mark here because I want you guys to tell me what a question mark is supposed to be. Okay, I'm going to use the same trick here. The idea is I want A to end up with the address of N again so that I can dereference that so that A becomes N again, and then we decrement it twice so that register A is N minus 2. Okay, so we can push it on the stack. So now we do a decrement D, store to D, register A. So we're pushing N minus 2 here, and so on. Okay, so I'm going to stop here and go back to line 29 and ask you guys, what do you think is question mark? We had something like this before. We computed the value of N from D already. It's 2. How come it's 2 and not 1?
Because the return address.
No, that is not the reason. Yep.
Because for the stack diagram we have at the very top, we added one more thing to the stack.
Yep, because now exactly. So if you want to look at what the stack looks like at this point, so I'm going to put a 2 here. But if you want to know what the stack looks like at this point, okay, now this part, I'm going to use the left-hand side for high memory address and the right-hand side for low memory address, okay? So the highest memory address is still parameter N. The next one is my return address, okay, the usual stuff. But then we have one more thing now on the stack, which is the saved value of f of n minus 1. And that is what D is pointing to. D is pointing to the saved return value of f of n minus 1. So that means if I need to get back to the address of n, and this is what D is pointing to, I need to add 1? No, I need to add 2 to register D in order to get back to the address of parameter n. Yes?
That's what I was saying. The return address is in between the number we have and the number we want to get to. So we times 2.
Okay. I see. I did not interpret it correctly then. All right, so we got the parameter pushed. Now it's just the usual boring stuff to get the return address pushed and then jump to the beginning of the subroutine. So we have an LDI, we can use A again. F return from minus 2, N minus 2 actually, so better spelled correctly. And then we define the label here, F return from N minus 2. Okay, and then we do a store, a decrement D, to allocate the stack, do a store to what the stack pointer points to. This is basically pushing the return address on the stack. Don't forget the unconditional branch because otherwise nothing happens. So we have to go back to the beginning of the subroutine that we're calling, which just so happens to be the subroutine that we're in. Okay? So the mechanism of calling doesn't change at all, whether it is recursive or not recursive. Is that okay? That basically was the idea of the sample program that I gave you guys that involves Johnny, Jerry, and what? Huh? Peter, that's right. Peter is the 12th Doctor, that's why. Johnny 5, from Short Circuit. And then Jerry is the actress of 7 of 9. 5 plus 7 is 12. So Peter is representing 12 because he is the 12th Doctor in Doctor Who. There's reasoning behind everything. It's just that sometimes that reasoning can be obscure. Okay, so at this point, when we get back from the second call, which is f of n minus 2, I can increment D because that value, that argument is definitely of no use whatsoever at this point. And right now, the return value of f of n minus 2 is in register A, but I need to add the return value of f of n minus 1 to that. So that means at this point, it's a good time to retrieve that saved return value from the stack. So when you're retrieving, you always want to load before you increment. So you want to load it into a register. Anything other than A or D is fine. So I would pick B in this case. And then increment D. So basically this is popping f of n minus 1 to register B. I'm restoring that value into register B. So now we just need an add instruction here, adding register B to register A. So now A is f of n minus 1 plus f of n minus 2, and that's it. So that can merge to fn, which is the usual code to get out of a subroutine. So that involves LD again, to register B, because register A has the return value. We don't want to overwrite it. Increment D to pop the return address. So we are popping the return address to register B, and then the JMPB to continue execution in the caller. Are there any questions about this code? And you can see how I leave behind, a little bit of a comment. Yep.
Is it common with any other calling conventions to, instead of like having to kind of like avoid reusing registers between calls, to just push all of your registers to the stack before a call and then pop them all back into the registers after?
You could do that, but it is the responsibility of the caller to do that. So you still have to make the assumption that the callee can utilize all of your registers.
So like you writing the function that like is around the function you're going to call, you do that yourself as like padding around the call.
Right. In other words, if the process to recompute things that you have already stored in the registers is lengthier than the process of pushing and popping, then you should push and pop. On the other hand, if it's easy to recompute, like in this case, then you can just kind of go like, okay, the registers will be overwritten, but I can just recompute the things that I need to be in those registers later. So it's a trade-off. If you've already gone through like some kind of approximating function and whatnot, and now you have to call a subroutine, I would say push it on the stack, because otherwise you have to recompute, and that can be a lengthy process. Okay. Yep.
When do you call f return from n minus 2?
Say that one more time.
When do you call f return from n minus 2?
I did not call f return from
So then how do you ever get to line 40?
line 40. Well, you mean this line here?
Yeah.
That's a good question, but it is a concept that we probably should get at this point.
I'm just saying when.
Doesn't callback includes the return address that refers to that register and puts that on the
But
stack
it
so you
jumps
can
to
come
that
back?
at the end.
The subroutine gets to that label because of the sequence of instructions at the end of the subroutine. Now, that subroutine turns out to be the subroutine that we are talking about, but it doesn't matter because every subroutine would do that. So are we good so far with this? Nope? Yes? Move on? Okay, let's move on to main then. Okay, so main is down here. Main has got a local variable, so I have the decrement D to allocate for that local variable. And then we call f of 13, so we have a LDIA 13, decrement D again, and then store to DA. So we are pushing the number, the constant 13 on the stack. LDIA with a return address. This is main return from F, okay? Main return from F. Oops. I'm using, there we go. And then we decrement D, store. This is pushing the return address. And then we do an unconditional branch to the subroutine that we're calling, which is F. When it returns, we basically want to increment D to get rid of the argument that is on the stack right now. And then D will go back to point to local variable X, which is really handy because to store the return value of f of 13 into X is now just a single store instruction because D is pointing to local variable X and A has the return value from the call to Fibonacci. So we are all done, basically. But in order to be a little bit more consistent, we have to now put a 0 into register A, and then increment D again to deallocate the local variable. If main is not it's not special in this case, then I would still use the 3 instructions at the end of a subroutine. Okay, so yes, so to many people, all of this stuff, all the way line 63, 64 really are not needed because of the special status of main as a quote unquote subroutine. But if I do it like this, then if I want to turn main into a general subroutine, it would just be substituting the halt instruction with the 3 usual end of subroutine instructions. So I don't consider main any special, in any way more special than any other subroutines except for the return sequence. But the way I utilize the stack to free and allocate items from the stack is identical to any other subroutine. Is that okay? All right. So let's go ahead and give it a try. Okay, Control A, Control C. Go to my assembler. There we go. Go to source. Paste. There we go. Okay. And let's see. We go to RAM file. Okay, everything is good because otherwise this would not be a v2.0 raw. File, download as. Oops, I picked the wrong extension. Do it one more time. It will still work, it's just that I want to keep using the same consistent, extension here. We'll call it, Fibonacci.csv, save, replace. And the simulator is still running, so let's check that. Control R to reset the simulator itself, and then we want to reload the image itself. There we go. So now we can go at full speed. Okay, it's going to take a while, as I said. Now, as it goes in full speed, we can also look at RAM content and just kind of watch the things go back and forth like that. Okay, Control K. Oh, I have to do it from here. So I just thought that's kind of cool. It will take a little bit longer on my computer because this is a slower computer compared to.
Almost looks like a wave of numbers.
Yep. Mm-hmm.
What did we load what parameter did we pass into that?
Say that one more time.
What value did we pass for that parameter?
13. Yep. 13. Oh, okay. Came back with an E9. So the question now is E9 the correct answer? So what is E? E is 14. 14 times 16 plus 9 is it 233? Because 233 is the Fibonacci of 13. Well, there's a quick and easy way to do it. You can run the C code too. You can run the C code and figure out what is the F value of 13, but you can also just kind of look it up. Fibonacci of 13. So the Fibonacci of 13, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the Fibonacci number of 13 is 233. So the program does work correctly and figure that out. Are there any questions about the code that we just did? Let me switch back to the assembler part. Are there any questions? It is by no means fully optimized, but it is correct. Okay, I did There are a few things I can do to kind of make it slightly more optimized, but it's not, as it is right now, it is still okay. Is that okay? All right. Okay, so we got about 35 minutes left. So what I will do is I will give you guys a kind of like a jump start for your homework assignment, because it was assigned on Tuesday, 2 days ago. Some of you have done some significant work already, and some of you may not have time to do it. So we'll go ahead and start with that particular program and see what we can do with it. So we look at struct.zip. This is the wrong class, but it's the same file. So I can just go back to this class too, just to be sure that we are using exactly the same file. So we go to this class, scroll all the way to the bottom, and download the struct.zip. I have that file ready, but I can, oh, okay, it just renamed it. That's okay. And then we'll do an unzip of struct in parentheses 1, and I'm going to rewrite all the files just to be sure that I'm looking at the same thing that you'll be looking at. Okay. This is the C code. Are there any questions about the C code of this particular program? Okay, no questions. Now, there is one thing that you might want to do with the C code. Yep.
So the line, the dereferences array incrementing, what is that actually? Why are we doing that one?
You mean this line here?
Yeah.
So line 15 is to increase. Okay, so I need to scroll down a little bit to show you why we need to do that. See, p sorted is a pointer to an unsigned 8-bit integer. So p sorted is actually the pointer pointing to the next byte in sorted that I need to overwrite. So every time I write something into the array sorted, I'm going to increase p sorted so that I'll be ready to go to the next location. So that's why we are on line 15, we are incrementing whatever array points to. Because what array points to is really just p sorted. But the previous line on line 14 is changing what p sorted itself is pointing to, which is inside sorted. Okay? So the first thing, if I were you, the first thing I would do is to run this code in C, in GDB, just so that I have a general idea of what is being passed, the relationship between p sorted, sorted, and in which order are we writing values into sorted. Because the C code does work. I mean, this is fully compilable and workable code. So I would use GDB to help me understand the correct behavior of the program first before I try to code it in assembly, because then I can look at the assembly code and go like, okay, is it resembling what the C code is doing? Okay. So I'll do it first. Okay. So, yep. Question.
I just had a question. So I was just tracing out how all the integers are stored into the array.
Mm-hmm.
And so would it go, isn't it stored in the array by like 3, 4, 5, 9, 10?
Yes.
That's how it's ended up putting. How would you traverse the array to output those values? Because when I tried to do it, just like a little for loop, it like just put out gibberish.
Say that one more time. How do we traverse?
How do you just like output what's stored in the array?
In GDB, you just say print sorted. Yeah. Now the problem is because because the type of the elements in sorted is byte wide, so GDB being a smart ass, says oh those are characters, right? So when it tries to print 9, it will print the quote unquote character corresponding to ASCII 9, which is a tab, and then 10 is line feed. So if it attempts to print line feed, it will either print \n, which has an ASCII code of 10, or it might actually print the line feed, which gets you to the next line. So that is why. But GDB actually will give you the \/ notation. So I'll show you guys what I mean by that. So the program compiles, and then we use gdb a.out because that's the default name of the executable. You guys can use code blocks, you can use any IDE if you want to. The idea is you want to track down what the C code is doing so that you have an understanding of how this thing works. So I will put some breakpoints, okay? So I will put a breakpoint in at least at the entry point of traverse, okay? That's definitely important. Let's see, what else do I want? That may be all I want, but I'm going to put a breakpoint on line 35 as well, okay? Right before the first call to traverse. Okay, there we go. So run the code. Now we are at line 25. This is right before the first call or the first invocation of traverse. So at this point, okay, I want to print out what is in sorted. And it prints a bunch of gibberish, blah, 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 because sorted is an array of 50 characters, basically. So GDB just is attempting to print it as a string, except most of those characters are non-printable. So that's why it says \001, which is just 1 as an 8-bit unsigned integer, \000, which is really just 0 as an 8-bit unsigned integer, and so on and so forth. But you can always, if you do not like this, you can always just say, okay, tell me what is the first element of sorted, what is the second element of sorted, and so on. So this way, it will give you the actual unsigned integer representation, even though it still wants to give you the character representation, but it's not a big deal. But what is kind of more important is what is p sorted. So p sorted is a pointer, right? Where is it pointing to? Well, the initialization says that it is initialized to sorted. So that means p sorted initially is pointing to the first element of sorted. And then it is passed into the subroutine. Is that okay? All right. So I'm going to continue execution, which will basically stop right away because I put a breakpoint at the entry point of traverse. So it stops right away. Cool. This is exactly what I want, where I want it to stop. Because I want to know what is array. Okay. Print array. Array is, okay, you can see it's a double asterisk. It is a pointer. It is a pointer to an 8-bit unsigned integer. That's how you read the type of something. So now I'm interested in, okay, what is it pointing to directly? So you say, okay, what is array pointing to? Array is pointing to that thing. I think we have seen that a little bit earlier, haven't we? Right here. So array is pointing to p sorted. What is p sorted pointing to? Well, double dereference. But where is that? I know it seems kind of silly because we are taking the address of double dereference, but it's okay. We can do that. How do we know this is actually the first byte or the first element of sorted? I forgot to check where the array is. So how do I know this is actually the first byte of sorted? Now we got a clue here. Yes, we got a clue here. But how do I confirm at this point that it is this is the address of the first byte of sorted? So this is where your frame comes in handy. Frame allows you, okay, frame and BT together. Okay, so I'll show you BT first. BT shows you how we got here from the perspective of nested function calls. So this is showing me that main is calling traverse. So it gives me the current frame, the current subroutine that you're in at this point is always frame 0. So frame 1 is the caller, and then frame 2 is the caller of the caller, and then frame 3 is the caller of the caller of the caller, and so on. So you can actually track everything down to main. in any program using BT. Then you can use a command called frame to change your frame of reference. In other words, I'm not interested in traverse anymore. I'm interested in what is in main at this point. So by saying frame 1, we are now changing our frame of reference back to main. I now have access to everything in main now. So now I can say, oh, where's array? Oops. No symbol array. I didn't call it array, I called it sorted, sorry. So sorted. Aha, okay. But it doesn't show me the address. Particularly, I'm interested in the address of sorted bracket 0, which is the first element. There we go. Do we have a match? We do have a match. Is that okay so far? Because this is before I do anything in traverse, I just need to understand what is being passed to the subroutine. Is that okay? All right? All right, so I'm going to change the frame back to frame 0, which is in the first invocation of traverse. And I can single step. This is in GDB, and we can just go ahead and single step. The first thing is, what is PTR? PTR is pointing to a node structure. What is the structure look like? Okay, this is what the structure looks like. The value is 5. The left, which is a pointer to another structure, is this address, and then R is another address. Okay. But right now we are on line 11, which is basically asking, is pointer null? It is not null, it's pointing to something. So when we single step, we get into the first recursive call. The first recursive call is going to traverse the left-hand side, which is the L pointer here. So it's going to push, an array is pushed the way it is on the stack. Okay? So we are not dereferencing, we're not adding 1, we're not doing anything to the parameter. We just pass it as is to the next invocation. Is that okay? So from the perspective of this line, which is line 13 of the C code, whether array is a pointer to a pointer, a pointer to a pointer to a pointer, doesn't even matter, okay? Whatever my parameter is, I'm just making a copy of that, pass it along, okay? So there's no need to understand what array really is at this point. Now later on, yes, we do need to know that, but not at this point. So if I single step now, it is going to go into the second invocation of traverse. What is the stack going to look like? BT again. So we can see how we got here. Main is calling traverse the first invocation on line 35. The first invocation of traverse is calling traverse again on line 13. We are now at the entry point of the second invocation of traverse. Is that okay? But the really nice thing is it also shows you the parameters of each invocation. Is array changed between the first and the second invocation? Array itself as a parameter. It's not changed. If you look at the parameter array, it ends with E188. When you look at it again in the second invocation, it's the same. In other words, we are really just passing that parameter along. Okay? So now we ask, is PTR null? Yeah, definitely not. Okay? So single step, we get into the subroutine again. And this time I'm passing the L member of the structure pointed to by PTR recursively as a parameter. So I'm interested in, okay, what is the structure pointed to by PTR? Oh, okay, L is null this time. It is a 0. But we are still passing it. We are still doing the recursion. It doesn't do any harm because we'll check later. So single step one more time. This is the third invocation of traverse. So if I do a BT, it shows us that this is the third invocation. Main called traverse, traverse called traverse, traverse called traverse. Okay? But it also shows you at each level what is being passed as array, what is being passed as PTR. And you can always double check and say, okay, this PTR here, which n are we talking about? Is it n1, n2, n3, n4, n5? Well, you can always just look at this. I mean, GDB does a pretty good job of, hey, I recognize this address. It is global variable N1, N2, and now it is null. So that means, in this particular case, in the third invocation, PTR is null. So we're going to skip everything, okay, all the way to the end and just return to the second invocation of traverse. But when we get back to the second invocation of traverse, this is the code that is after the first recursive call. Is that okay? Which is going to update what p sorted is pointing to with the value member of the structure pointed to by PTR at this point. Whew, that's a long way. And what do you think that value is? We are dealing with N2 at this point. If you look at the initialization of N2, what is the value of N2? 3, that's right. So we're going to overwrite the first element of sorted in main with a value of 3. Is that okay? So if you're not convinced, okay, then you can check everything. You say, okay, what is PTR pointing to? Oh, okay, PTR has a member value that has a value of 3. Okay, cool, the right-hand side is done. What am I overwriting in this case? I'm not overwriting array, which is a parameter. I'm not even overwriting what array points to, which is p sorted in main. I am changing what that is pointing to. Is that okay? So to understand what we are dealing with, you print array, you print star array, you print star star array. We are changing, so after the update, this expression would change. That is the idea. Okay? So we single step, okay? We single step first, and then we print those 3 things again. We print array. Is it the same as before? Yep. We print star array. Okay. Is that the same as before? It is. Okay, because when you look at the actual address, it is the same. It is the content at that address that has changed. So the only thing that really has changed is star star array. Okay? So looking into the C code using the assembler, using GDB like this, gives you the insight that you will need in order to debug the assembly code. Okay? All right. Single step. So I have just executed this instruction here. So once again, I look at array. Did I change the array, the parameter itself? Nope. Array stays the same throughout these 2 statements. Okay? Nothing is changed in array. What about star array? Star array used to be a B0, now it's a B1. In other words, I have just incremented a pointer, but that pointer is not array itself, it is what array points to. Okay, but does that mean that we have just incremented p sorted? Because array points to p sorted, and array is never changed, so it should still be pointing at p sorted. So p sorted should not be changed. How do I check that? BT, right? Because I need to I need to go back to the context of main in order to check what is p sorted pointing to. So I do a frame 2 to go back to main as my frame of reference. And now I can print where is sorted, okay? And what is p sorted pointing to? It used to point to the very beginning of sorted. Now it's pointing to the second element of that array. So is that okay? I mean, is this helping you to kind of get a better understanding of the C code first? Because without a good understanding of the C code, the translation into assembly would be kind of like really hard. Are we good so far? Yep. Okay. So I'm going to kind of fast forward here. So I'm going to delete, I'm going to list main because I need to put a breakpoint at the very end so that we can actually see what is happening to the array itself. But if you are in doubt, you should put breakpoints and double check, slow down the whole process and know what the algorithm is actually doing. So I'm going to delete the first breakpoint, delete the second breakpoint, and leave only the last breakpoint in the code. Continue execution. Now we can say, okay, now it's all done. We're back in main. And I want to print the entire sorted array. And we can see we have 3, 4, 5. This is a tab character, which is ASCII of 9. So \t is basically 9. \n is the line feed character, which has an ASCII code of 10. So we are basically getting 3, 4, 5, 9, 10 into the array. Is that okay? Yep.
So like, is the reason why that array is so long is because you picked like a random number to like, so you weren't giving away the stuff on campus?
Yep.
Okay.
Now the answer is disclosed, right?
Well, I mean, that's not the answer. We just know. Like,
I mean, the answer to that question.
Yeah.
oh, yeah.
Which was really obvious to begin with. Yes. Okay, so do we have any questions about the behavior of the C code? All right, so when you are writing your assembly code and you go like, okay, I want to go slow, I don't want to write everything and then test it with this complex tree structure, what can I do to make it easier to debug, okay? All right, so we'll go back to the C code. I'll give you some ideas of how you can change the way you test the program to make it sure that you get the basic stuff first and don't even deal with the recursion, okay? So we'll look at struct.c. So I think I talked about this already. The first thing is don't worry about the recursion. Get rid of the recursion part, okay? In other words, give it a particular n1 or give it a 0 even, okay? So go to your main program here, locate a code that is responsible for this one. I wouldn't just kind of delete or comment out something. I would just make a copy first before I start to make changes. Get this done first. In other words, you want to make sure that nothing is going to happen. It returns properly. The stack is fully balanced and nothing is corrupted with this code. Because in this case, there's no recursion. In fact, it doesn't even do a single thing because PTR is null, so the conditional statement would not execute the then branch at all. It just goes all the way to the end of the subroutine. It just returns doing absolutely nothing. So if your program does work correctly in this case, it gets back to main, the stack is fully balanced, and all that stuff is working, then at least you got the calling, the returning, all that stuff done correctly. That's good confirmation, because if that is not done, if that stuff is not done correctly, the rest is kind of pointless. Is that okay? All right. Then the second thing you do is to say, okay, if that works, I am going back to the original code, like that. But I will still have a subroutine that has no recursion like that. Okay, so you're not worrying about the recursive part. You're just saying, okay, according to this, what it is supposed to do. What do you think is observable if your code is working correctly, if the program is modified the way it is right now? Sorted would only have one location changed because there's no recursion. Only the first element is changed. And what should it be changed to? 5, because 5 is the value of the structure named n1 here. What about p sorted? P sorted would be incremented by 1, so it should point to the second element of sorted. Okay? If the program doesn't do what I just described, stop, debug it. Don't worry about the recursive part because that's not part of your worry at this point. Is that okay? So let's say this part works okay, it seems to be fine. We are overwriting and the first element of sorted with the value of whatever the PTR is pointing to, and p sorted is incremented correctly. Okay, if that works, then you can start to do the recursion, because then you can start to uncomment or add code to deal with this part here. But if you add code to deal with the recursive part, I would change this code a little bit here. So I'm going to change main again, and I'm going to pick one node that is easy to deal with. N4 or N5 would do fine, okay? But I would just pick one of these two. Why do you think this is easier to debug compared to N1? It's two null pointers. So we know when it does do the recursive call should do absolutely nothing. Okay? So that means doing this with or without the recursion should give me the same result as far as sorted is concerned and p-sorted is concerned. It should do exactly the same thing whether I have the recursive call or not. Okay? If that is working correctly, then I would be slightly more ambitious and change this N4 to, let's say, N3. Because N3 only has recursion that actually does something on one side. Okay? If that works correctly, I change it to N2, which exercises the other side. Okay? Now those two sides are pretty symmetric. So that means if you did it correctly and you understand the concepts, it should work. Okay? Whether it's left-hand side or right-hand side, the code is very symmetric. But if one side works and the other side doesn't work, that means you have to compare the code between those two branches and understand why it is not working only for one branch, because they should be about the same. They're not identical, but they are very close. Okay? If that works, then we are fairly confident that the whole thing is working. Then you can go back to N1, because N1 is going to do multi-level recursion on both sides, But if you debug the program like this, I think it's going to be a whole lot easier than starting with N1 itself. I'm sorry for those of you who have already started and almost got the whole thing done or have the whole thing done. But that is a learning process too. Without me explaining this first and you got it done, you are actually doing a lot more studying than the rest of the class. So are we okay so far with this homework assignment? The process of debugging. We got 8 minutes left, which is great because now I can show you how I would get started with the assembly code. Okay? And I'm not going to give away actually any code, but I'll tell you how I would do it. So I think we have a struct1.ttpasm, which you can assemble, and then you can just get that the assemble code to run. So I would do that. Let me just show you what it looks like. So this is the starting point that I want you guys to use. But when you look into the subroutine of traverse, instead of giving you a return right away, I put a hold here for a very specific reason, because I want it to stop there so that you can see what is on the stack, what is in memory at the entry point of the first invocation of traverse, because that will give you some idea of what we're dealing with. Is that okay? So I'm going to assemble the program as it is right now. Okay, mouse pad. It'll be kind of cool if there's a command line program to copy the content of a file directly into the clipboard, so I don't have to do something like this. Pretty sure somebody wrote a program like that already, but I just have to find it. Assembly. Let's see, go to source. Control V. And then we go to RAM file. Okay. I know what's going on. It didn't overwrite enough lines, so there are some leftover lines with some leftover references to stuff that is not currently defined. Okay, there we go. Go back to RAM file. It's all good. Download as CSV. This is struct.csv. There we go. Then we go back to Logic Sim. Right here, reset the whole thing, Control R. Reload the memory with struct.csv now and run the program. This one's not going to take much time because I put an entry point at the very beginning of Fibonacci. Traverse. So we're stuck now. Control K, stop the clocking, and go to edit content. And even this is showing us quite a bit of useful stuff. Okay. First of all, we see CD at location FF. Okay, let me point out where we are talking about. See the CD here? Explain it. Because we should be able to explain everything that we see at this point. Okay, if not, we need to stop, slow down, and go back and review some material. Where is CD? This entire row is C. So we're talking about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. That is D, E, F. So this is D. This is CD. What do you think that is?
I think it's star array.
It is array itself. It's sorted. Sorry, it is sorted in main. Okay, so sorted in main is starting at location CD. Then what is at location FF? It's P sorted. Okay, so P sorted of main is at location FF. It is a pointer pointing to the beginning of sorted as an array, which starts at location CD. Is that okay? So that is from main's perspective. Then what is that junk, to the left-hand side of the first byte of sorted? In other words, we know this byte is the beginning of sorted or the first element of sorted. So what is this stuff here? Well, when we call a subroutine, what do? We push the arguments first and then the return address, right? This is the second argument. Oh, the second argument is supposed to be what? The address of P sorted. This is P sorted. This is the address of P sorted. What about this guy? It's my first parameter. It is supposed to be the address of N1, right? The address of N1. So you locate 1B. This is the entire row of 1. So we have 1B. This is 10, 14, 18, 9AB. That is 1B. Does that make sense? I mean, the first byte of that structure is a 0, 5. N1 does have a value of 5, and value is the first member of that structure. So it kind of makes sense that 1B is pointing to the first byte that it points to is 5. Okay, that's the best way to put it because it's officially pointing to an entire structure, which is the 0, 5, 1E, and 2, 1. Okay, what about this 1, 5 here? What is the last thing that the caller is going to push before jumping into a subroutine? The return address. Okay, well, how do we check that this is actually the return address? So we go back to the assembler. We go to the Assemble tab. And in the Assemble tab, the first chunk of stuff is not really helpful. So I would just kind of scroll until you see column U as the first one. And then you just kind of scroll down to find out what is at location 15. This is location 15. Column W is what you want because column V is in decimal. Column W is in hexadecimal. And that turns out to be the label of main return from traverse. Oh, okay, so it is the return address. Cool. So this is the first step, is just to say, at the entry point of traverse, what do we have on the stack? The tricky part about this homework assignment is what exactly is array? Array itself is a pointer to an unsigned char. In the window here, I'm going to point it out, okay? This is a pointer to a unsigned char. And this is the best thing about screen recording is it actually records as I move the mouse pointer and stuff. Is that okay? Now, of course, when you want to write your notes, you might want to actually use some actual arrows to indicate what is pointing where. But are there any questions, in terms of the conceptual part of this homework assignment?
So the point of we're actually changing the address of is CD or
That is correct. So as the program executes, this CD will become C, E, C, F, and so on. But only the first 5 locations should be used. So that means CD would increment to C, E, C, F, D0, D1, and then D2. Okay? When it is all done, then these 5 bytes will be used, but the pointer will point here because it's always pointing to the next location that will be used. But since we only have 5 nodes in the tree, it will only use the first 5 locations. The rest are basically wasted. In fact, I just answered one of the questions in the quiz like 20 times today. I didn't actually count, but I think a lot of times in different forms. So any other questions about this program? So this is not an easy one to write. It's not an easy one to debug, okay? So what you need to do is if your program, so when you run the program, you want to observe what it is doing to memory. If it is going like this, okay, if it's chewing up space in this, in a reverse order, and it doesn't seem to end, Control K, stop the clocking, okay? Stop the clocking before it starts to clobber instructions itself. And then what you do is not to just kind of like throw your hands up and go like, I have no idea what is going on. Look at the content that is overwriting, because it is always going to give you some clue as to what the problem might be. Okay? The way it is overwriting stuff on the stack, even though it looks like gibberish at first glance, it is not gibberish. It is always going to be a little bit indicative of why your program is not working. So you got to remember what it is supposed to do and then compare to what you're observing. That is how you can start to debug the program. If all fails, okay, if you look at this dump of memory and go like, I have no idea what is wrong with the program, use the log, okay? So when you use the log, you need to log I would recommend logging all the registers, A, B, C, and D, the program counter, and also the bytes that you think that it should definitely overwrite. This location, for sure. These 5 locations, for sure. And then also, at least a few bytes, in this direction, because those are the bytes that will be used for the invocations and whatnot. Because you need to find out which instruction is overwriting what register or which memory location in what way. That is what you need to track down. And the first time or the first thing that goes wrong is basically the first thing you need to fix. Is that okay? All right. So we're going to head back to the lab for the second lab. And I will be able to answer some email if the question is specific enough. In other words, if the question is, my program is not working, tell me why it's not working, I cannot answer those questions. Well, I will answer that question with another question like, can you be more specific?